Have you ever wondered how an AI can know what happened yesterday, even though it was trained like months ago? Well, the answer is this really powerful technology that acts as a whole new kind of memory for AI. Today, we're going to pull back the curtain on vector databases. It's a great question, right? I mean, most of the big AI models you use were trained on a static snapshot of the internet. They have a knowledge cutoff date, so how can they possibly talk about recent events? It all comes down to a really clever way of searching for information that goes way, way beyond a simple keyword search. So, to really get how AI pulls this off, we've got to first talk about why the old ways of searching just don't cut it anymore. Okay, so on one hand, you've got your standard keyword search. If you search for sunny weather, it's literally looking for documents with the exact words sunny and weather. But what if the best article out there says something like clear skies and warm temperatures? Keyword search is probably going to miss it. And that's where semantic search comes in. It doesn't just match words, it gets the concept, the vibe, the meaning behind what you're asking. It just knows that sunny weather and clear skies are talking about the same thing. Right, so how in the world do you teach a computer to understand meaning? Well, the secret is to stop thinking about data as words or pictures and start thinking about it as numbers. Okay, let's dive into this because it's really cool. The process is called creating a vector embedding. You take a piece of data, could be a sentence, a photo, anything, and an AI model translates it into a long list of numbers. We call that a vector. Now, the magic trick here is that the AI is trained to group similar concepts together. Think of it like a giant library where all the books about, say, space exploration are put on the same shelf. They become neighbors in this big mathematical space. This right here, this is the classic example that just blew everyone's mind when it first came out. Researchers found that if you take the vector for king, subtract the vector for man, and then add the vector for woman, the resulting number is incredibly close to the vector for queen. I mean, come on. This shows they're not just storing definitions, they're actually capturing complex relationships, all with math. But here's where things get really interesting. That technology has evolved. The early embeddings were static, so the word bank always had the same vector, no matter what. But modern AI models, like Google's BERT, they're way more sophisticated. They create what we call contextualized embeddings. And check this out. This shows you that evolution perfectly. A modern AI can actually tell the difference between, I need to go to the bank to deposit a check, and we had a picnic on the riverbank. It generates a totally different vector for the word bank in each sentence because the context is different. This is a huge leap in an AI's ability to understand nuance. Okay, so we've got this amazing new power to search for meaning, but it comes with a brand new, absolutely massive problem. We have to do it at an unbelievable scale. I mean, think about it. You've got modern apps that need to store and search through embeddings for literally billions of documents, images, or products. That's billions of these super complex, high-dimensional vectors. So if you want to find the most similar items in that massive pile, how do you do it? Well, the most obvious way, right, is just brute force. You take your search vector and you measure its distance to every single one of the billions of vectors in your database. And yeah, this will give you the perfect answer, eventually. But eventually is the key word there, and it's not good enough. For real-time applications like a chatbot or a recommendation engine, you need an answer now, not in 5 minutes. So comparing against billions of vectors one by one, it's just way too slow. It's totally computationally impractical. We need a shortcut. And the solution is this really clever trade-off called approximate nearest neighbor search, or ANN. The core idea is simple. In most cases, you don't actually need the absolute 100% perfect match. You just need a really, really good one. So ANN algorithms give up a tiny, often totally negligible bit of accuracy to get this enormous, game-changing boost in speed. So how does this magic actually work? Well, one of the most popular algorithms uses this brilliant, multi-layered approach. And honestly, the easiest way to get it is with a simple travel analogy. Imagine this. You need to get from New York to a very specific street address in California. You're not going to hop in a taxi and drive the whole way, right? No way! You start with the big jump, the flight. That gets you into the right general region. From there, maybe you take a train to get to the right city. And then finally, you grab a taxi for that last mile to the exact address. You start with these big, long-distance hops, and then you get more and more precise. And that is exactly how this incredible algorithm called HNSW works.
It stands for Hierarchical, Navigable, Small World, and it organizes all those vectors into a multi-layered graph. The top layer? That's your flight network. It's sparse, with long-distance connections that let you jump across the entire dataset in a flash. As you move down through the layers, the graphs get denser and more connected, just like the train and taxi networks, letting you do more precise, localized searching until you find the closest neighbors.
All right, so let's tie this all together and go back to our original question. We have this lightning-fast way to search for meaning. How does that help an AI know what happened yesterday?
See, the big problem with large language models, LLMs, is that their knowledge is basically frozen in time. They were trained on a massive but static dataset. Trying to retrain them every single day would be impossibly expensive. And without new information, when they don't know an answer, they can sometimes hallucinate, which is a nice way of saying they just make stuff up.
The solution is a technique called retrieval augmented generation. Yeah, I know, it's a mouthful, so we all just call it RAG. It's a fancy name for a really simple and powerful idea. Before the AI answers your question, it first retrieves relevant, up-to-date facts from an external knowledge source. And you guessed it, that source is very often a vector database.
And this is where it all clicks. When you ask a question, the system turns it into a vector and does one of those lightning-fast searches in a constantly updated database. It finds the most relevant, up-to-the-minute facts, feeds them to the AI along with your original question, and then it generates an answer. This grounds the AI in reality and dramatically reduces those errors. The vector database isn't just a search tool. It's the AI's long-term, always-current memory. So this combination of technologies is fundamentally changing what AI can do. It's not just about knowing facts anymore. It's about having the ability to access and reason with the world's information in real time. Which really just leaves us with one final thought. Now that AI can access knowledge instantly, what problems are we going to solve next?